We did the first one with the Newman projection. Okay, video key, video key. Newman projection. Yes. Right here. We did the first one. Let's see how we did on the second one here. We got pictures of part of the unit group. Yeah, we can do substitution elimination chemistry. What do we have here? O minus, strong nucleophile slash base. Is it sterically hindered? Oh yeah, it is. Okay, big old wings on it. Sterically hindered, that's just solvent. Okay, is it substitution or elimination? Can you do substitution here? You perhaps could. Up there it was no because leaving group from tertiary carbon. Here it's on what type? Secondary. Can you do substitution there? Yes. It's not as easy as primary or like methyl. But you can theoretically do it. This being heavily sterically hindered, is substitution going to be hurt by that? Yes. Sterics really hurts or influences substitutions. Right? This is the case where sterically hindered base is going to promote elimination. We said that near the end last time. Right? Okay? It looks like an elimination reaction to me. E1 or E2?
E2.
Why E2?
Strong.
Strong. If it's going to be a E2, we call it a base. Because if it takes an H, we call it a base. If it does anything else, we call it a nucleophile. So E2 requires a base, not a nucleophile. Yes, E2 because it's bimolecular. It's a bully base. Here I come. I'm not waiting for you to ionize. Okay, yes. This looks like an E2. Zaitsev or Hoffman product to be formed here. How many theoretical products are possible? Did you do that? Should be something good to do. How many theoretical products are possible here from doing a beta elimination?
Sure.
Right?
Sure.
I think it's 4. Because if you put double bond over here, remove H. But that's the alkene will be stereogenic. You can have cis or trans, E or Z. Same thing over here. You put the double bond in over here, remove this H, and it can be E or Z. Now, when I say theoretical, you're like, well, can all that really happen? Well, no. But those are 4 possible beta elimination products. And actually, only one is going to be your major predicted product. There are 4 possible. Double bond over there would be disubstituted. That would be the Hoffman product. Double bond over here would be trisubstituted. That would be Zaitsev. Okay. What are we going to get, Hoffman or Zaitsev? Why Hoffman? Yes. And this is where some of your answers will vary. Some professors of books will say, hey, it's very sterically hindered, so instead of substitution, we're going to get elimination. Yeah. But then they kind of stop there and then they give you the Zaitsev product. Some books and some instructors then take it a step further and say, okay, of the elimination product, are you going to get Zaitsev or Hoffman? And with sterically hindered, what do we say? You tend to more get Hoffman. And that's where it can be some gray area. Sometimes even for me, I may say, hey guys, here's the question. Show the Hoffman product. And take some of the guesswork out. Or maybe this. Why don't we do this? Why don't we show the Hoffman product and Zaitsev product? But maybe the question is presented that way. I kind of agree. I think Hoffman is going to be the product. But we need to show the Zaitsev because showing the Zaitsev requires us to do Newman and stuff. So we're going to do both. What would the Hoffman product look like? Anybody have it? You're showing, you said or. You've got 2 stereoisomers and you said or?
Yeah, I just wanted to show
But which one's going to be formed though?
I was thinking that either of them because there's two H's on that suit. When I did the new projection, I thought that both would be formed.
Okay. One thing he said there was there are two H's here. I'll give you a take home, and I may have to later explain it. Whenever you have two H's on the beta carbon, you don't have to worry about doing a Newman and having anticoplanar. Because guess what? One of them can be, usually, unless we got something very strange going on. How many beta hydrogens over here on this beta carbon? Only one. When you only have one, that's when you really have to look at it close. Because we got this H and that Cl have to be anticoplanar when the elimination takes place over here. Yes, one of these also has to be anticoplanar. But since you have two, you essentially have a choice. And when you have a choice, what's going to win out? The best product. So the answer is the best product will be formed. Which one's that going to be? The alkenes is going to be with the biggest groups, trans. Opposite, anti. Okay? I'll show the product here. We're going to put double bond in over here. And that's going to give a methyl, and it will give a remaining put double bond in here. Double bond in there between the two carbons. But my groups on my alkene are trans. Okay? Or E, I'll just say trans. Okay? That's the Hoffman product. Whenever you have two H's, you don't have to worry about the anticoplanar stuff, because one of them will be, and since you have a choice, just show the best product. Okay? But what if you were asked to show the Zaitsev product, or you thought it was a Zaitsev? Double bond's going to be put over here, right? By the way, this still remains chiral because we did nothing here. We put the double bond in over here, it's going to be double bond over here. We have an ethyl there. And then on this carbon, which the double bond is over, we got a methyl and an ethyl. Methyl and an ethyl. But guess what? That's stereogenic. And we can also have the two ethyl groups, cis, where here they're trans, right? These are stereoisomers. If you do E or Z, you'll see that this is E, and you'll see that this is the same side. The two priority groups are the same side. Which will be the product? Well, here we got to look at it closer, because you don't have a choice. This H has to be anticoplanar. I'm going to erase this here. Let's draw this in a Newman, because to me that's the best way. If you can see it some other way, great. I'm not going to show you 3 or 4 ways. There may be other ways to do this. I'm going to show you the way I recommend. I recommend drawing a Newman with these two carbons. Let's look down this front carbon, back carbon. What do we see on the front carbon coming straight down? A methyl. Let's draw in that, clarify that with an ME. What's on this carbon coming to my right as I'm over here? Yes. H. What's on the carbon going behind the board if I'm over here? It's on my left. Ethyl. Back carbon. What's going, chlorine what? Chlorine on the right. It's coming towards you guys. Okay? Also up. It's eclipsed with the H, isn't it? Yeah, because when we put it up here, it's eclipsed. It's right behind that H. The ethyl group on this carbon, boom, boom, ethyl is straight down. It's eclipsed with the methyl. And what else is on that carbon? Undrawn H, which is going back. But it's eclipsed with this ethyl. Careful, don't confuse your H's. This is the one we're talking about eliminating. That's on the front carbon. Let's call that HA. I didn't label those. HA is which one?
The right one, right?
That one. That's the one on the other carbon. That H is on the same carbon as the chlorine. That's the undrawn H. Don't try to eliminate that one. That'd be an alpha elimination. I don't know what type of product you would make you do that. That ain't gonna be right. You're doing beta elimination. Okay, right now the H is being eliminated in chlorine are syncoplanar. We need to rotate this so the H goes opposite. You can rotate it any way you want. I'll rotate the front. And I'll redraw this. And the front is now H. What's that, 180-degree rotation? The methyl goes up, is that right?
Yes.
Ethyl goes over here. The back did not change. Chlorine, H, and what else is in the back? The other ethyl. Now look at the H and the chlorine. They're in that plane there and they're anti. That's where the elimination takes place. Concerted. Bam, 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 all at the same time. Double bonds put in, and the double bonds put in, we see the ethyls are what? The ethyls are on the same side, and the methyl and the H are on the other side. Which one of these has the ethyls on the same side? What side is this? It's the same side. The H, the undrawn H and the methyl are on the other side. This is actually the product. And in this case, is that the best steroid isomer in terms of stability? No. It's better to have your bigger groups anti. But again, stereochemical requirement for the E2 must be met. That's a little strong. It's not that it must be met, but it's highly preferred. And it overrides any thermodynamic considerations. Okay, the transition state energy overrides thermodynamics. So it's really a kinetic argument. And once it's formed, it can't go backwards. So you can't achieve equilibrium. How are we doing with this, guys? Okay? Newman projections. That was test 1, right? If you go back and look at questions from test 1 in my workbook, I alluded to E2 elimination and told you we'd be doing it in test 3 or something. Maybe I didn't say test 3, but I alluded to E2 elimination. I said this question is important for E2 elimination. We'll see later. Okay? Well, guess what? We're seeing it now. And so we spent time learning how to do Newmans. Now we're using Newman to help what I think makes it easy to see this. Again, if you can rotate this and see it some other way, maybe some book presents it a different way, whatever works for you. I can only endorse one way. You don't want me to tell you 3 different ways, and we're just wasting our time. I'm telling you what I think is the best way. Okay, anything else here? Which would be the fastest reaction down here? We got hydroxide and we got the stereoisomers. Which one will give the elimination product faster? Anybody come up with a rationale here? Why the first one? Okay, what do we know about the iodine, the leading group? It has to be in what position to eliminate on this cyclohexane? Axial. It actually has to be axial, because only when it's axial will it be anticoplanar to a neighboring H. Okay. Question is really, which one of these will the iodine more readily be axial? Because if one compound, the iodine is more readily axial, it exists axial more often, it's going to be able to eliminate faster. Well, this goes back to chair confirmation. What was this, test 1? Okay. We want the iodine axial. Let's do A here. The iodine is axial. Where's the tert butyl? It's here. Not the adjacent carbon, but one away. And I won't worry about it afterwards, even though we could possibly discuss that right now. I may end up with a mirror image. I'm not going to worry about that right here. In fact, I see that putting it here is right after I look at it. So check if you want to look at that. So the terbutyl here, is it axial or equatorial for A? Yes, it's also axial. Because the groups are cis. For them to be cis, they both are axial here, correct? Right? Cis. That's why they. Now let's look at B. Hopefully you can see, we can see down here. Now if the iodine is axial, where it has to be to eliminate, where's the terbutyl? It's actually equatorial. Because this is trans. Right? Okay, this is the conformation they have to eliminate in. Which one's going to be more likely in this conformation in equilibrium? Why trans? I mean, everybody see it because the terbutyl is happy, right? The big group is, the terbutyl is equatorial. What do you think this guy wants to do? Stay right there or do a ring flip? Ring flip? This guy's begging to do a ring flip. And at equilibrium, it ain't going to be existing like this to a large degree. This molecule is more often going to exist with a ring flip conformation with both groups equatorial. And can it eliminate when both groups are equatorial? No. So it's going to be very slow to do it. The answer is trans, right? That's the faster. Or we can say B. What other elimination product could be formed in reaction A? Is there another elimination product? It's a simple question. Yes. Instead of putting double bond here, removing this H, what could we have done? We could have removed that H in there. The double bond could have been put up there. I just showed you a different elimination product. But my question just alludes to the fact that there could have been some other, right? That is, there's two theoretical elimination products here. I don't know which is going to be favored, but the way I asked my original question, it doesn't matter. I asked my question about something else.
There will also be a second comment from you.
Yeah, I just asked you to look at A. It's the same thing, yes. I reckon I kind of, I see your point. It looks like maybe it's not going to happen for B. Yeah, the same thing for B. Okay. I'm doing this mechanism. I think they got this mechanism pretty good. First step, what do you propose? Here's a take home for you guys, and I haven't said this yet, and I say this several times in organic too. You're doing a reaction and you got like acid, okay? Acidic condition. Usually the first thing you're going to do in your mechanism is protonate something with the acid. Okay? Very common. What do you want to protonate here?
OH.
It looks like in the product the oxygen has left the building. I agree? It ain't there. Is oxygen a good leaving group? May make it a better leaving group. Protonate. Okay? Can I just skip that step? Everybody show protonation of an oxygen mechanism?
Yes, sir.
Okay. So I'm going to skip that here. You can't skip that on a test or anything. But everybody can get to that point?
Yes, sir.
Okay. What do you want to do next?
oxygen becomes clean.
What do you want to do next? What can you do? Do we have a nucleophile? Do you want to come in here and kick this off? No, there's nothing else there. Oh, this just leaves. Well, let's have a good arrow here. These electrons, because you guys are still showing arrow method and not saying these electrons. Because if you say these electrons, the starting point of your arrow should come from electrons. These electrons, let's grab them and sort of pull them away from the carbon and move them onto the oxygen. What does that give? Carbocation. Plus what? Plus water. We just synthesized water. We're going to save the planet. Okay? New water generated here. What's next? Resonance stabilized. We got to get another methyl over here. If you can do resonance, I would recommend always doing that in a mechanism, because doing a resonance structure can really change your molecule and make you see, oh, now I see it. Always consider resonance unless you see that you maybe don't have to do resonance. Let's do the old windshield wiper down. What does that give? Double bond here, there, here, carbocation here. That's a simple resonance structure, correct? You can also do resonance over here. It would actually be identical to that structure. Now, these are methyls, right? I can put CH3 on the end. I can just leave it like that. Or I can put Me on the end, which is common for me. Common for me, right? What can we do now? Can we get another methyl on the other carbon?
Yes.
What are carbocations prone to doing? Right. So what do we do? Like this?
No.
What's wrong with that? I don't know what that means. It looks like the charge is moving. Arrows don't show movement of charge. What do they show? Yes, these electrons between the carbon and carbon break free of this carbon. Let's grab them and yank them and pull them over here. And what does that give? One methyl there, the other one's now over here. Double bond there and there. And we're done?
No. There's a charge carbocation.
Carbocation here. There's no H there. How many H's on that carbon? None. None, 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 none. There's no H. There's only 3 bonds there. Okay? Yes, carbocation. Of course there is. We just did a carbocation rearrangement. A skeletal shift. What do you want to do now?
Water can take up the hydrogen.
We need to put in double bond. We have an H here. I told you 2 or 3 months ago, you got to keep track of your H's, right? Okay. Can we get home from there?
Yeah.
Yeah. How about this water taking this H, an acid-base reaction, and these electrons move in to make pi bond. That's the second step of a simple E1 elimination. Leaving group leaving, and then something takes the beta H in a fast step. Well, leaving group did leave, but we had other things going on in between. Now something takes the beta H in a fast step, put in the double bond. And what did we reform here? Yes, H3O plus. Now what did we actually form here? We actually did form water. This is H2O. That's new. So water is formed here, but it's also H+. That's H plus. That's just at the show of water. Okay, you got to get all that straight. How to show. This is an acid catalyzed dehydration reaction. We removed water, thus we formed water, but we also regenerated the original acid. Now I'm showing the original acid with the new water. Or you can keep this and say that's the new water and use an old water to take the H, and then you'd form old H3O+. In any event, we do form water here. The molecule, the starting material loses water. It is H plus catalyzed because we regenerate acid. So this is a E1 mechanism, but it involves resonance and rearrangement of the carbocation. But E1, like SN1, does involve the carbocation. E2 does not. E2 is a concerted beta elimination that requires a strong base because it's bimolecular, and only can strong bases or strong nucleophiles be involved in rate determining steps. What's the rate determining step of this mechanism on the board? Typically forming the carbocation. And I think for any of us that would be yes. I'm just leery of exceptions, but let's don't worry about exceptions. Forming the carbocation in these SN1 or E1, typically the rate determining step. Why did a nucleophile not add to this carbocation and give a substitution product? Water could add here. And just get this back there. Is this reversible? Yes, many steps that we do in our mechanisms are actually reversible, and I never say that. Because I'm typically going forward. But could water add here and get back to this? Yeah. Could water add there and give you a product with an OH there? Yeah. But this is a different outcome. One thing that drives this outcome is now the ring is what? Fully conjugated. Thank you. Good. Fully conjugated, and what we call fully conjugated cyclic compound is called what? Aromatic. Unless it's not. Because sometimes they can be anti-aromatic. Right? Anti-aromatics are also fully cyclic conjugated. You'll learn about that. You'll learn about that exception in organic 2. Anti-aromatic. But being aromatic sort of drives it to the elimination product. And water is the only possible nucleophile here. It all depends on what acid you use. What acid would you use? You can't just say, hey, give me some H3O+. There's got to be a minus. Would you use HCl for this, or would you rather use maybe H2SO4? Yes, why not HCl? Well, Cl minus will be more prone to adding to the carbocation and giving you a product with a chlorine in it, which would be a substitution product. We've talked about that many times, right? This is the type of acid you use when you don't want the anion to do anything. Okay? But again, you may see it presented very generically. Aqueous acid. Everybody good? Okay, where can we pick up at? Yeah. Which compounds below will give a positive silver nitrate test? Silver nitrate test. What's that about? How do you get a positive silver nitrate test? What type of compound will be positive? Well, let's look at that. Lewis acid. What's the definition of a Lewis acid? Lewis acid is a compound that accepts electrons. Accepts a lone electron pair. Okay. H plus is a Lewis acid. It's also a Bronsted-Lowry acid, we typically just call it this. Lewis acid. It's a clever way of making bromine a better leaving group. Well, any halogen. Is a halogen a good leaving group?
Yeah.
Yes. Okay. We typically don't have to worry about making a better leaving group. But sometimes you might. Look at this reaction. It's on a secondary carbon. Is this bromine going to readily leave and make a secondary carbocation? Not as readily as making a tertiary. What if it was on a primary carbon? Then we would say it's kind of doesn't want to leave at all. See, secondary is kind of mediocre. It can, but it might be a little slow, yeah? What if this reaction is too slow for you? Maybe you don't want to go to lunch earlier. How can we make the bromine a better leaving group? A clever way is to add silver ion. Okay? Ag plus. And it needs to be soluble. And in Gen Chem you'll learn that certain silver salts are soluble and some are not. Silver chloride, is that soluble in water? You learn solubility rules? Okay. What did you learn about nitrates? When I took Gen Chem, I learned that all nitrates are soluble. Silver nitrate is soluble. That's why we're using silver nitrate and not like silver something else. Okay? But silver ion, you've got to have a minus though. And it turns out that halogens love to complex with silver. And it almost looks like this is proton, and we can sort of show something like this. Now I'm hesitating a little bit of if I don't see this shown this way as much. I don't know. I don't have any reason not to. Let's just show it's silver here. Bromine has two long pairs. Bromine is actually now positive. And isn't the silver accepting a lone pair? And so the silver ion is a Lewis acid. And the silver is now neutral because there it owns no electrons other than some that are not being shown. But now with the bond, it owns one of these, so it has one more. And if something is positive and has one more electron, it becomes neutral. But the bromine is now positive. Now, is the bromine a better leaving group now? Yeah. Now the bromine's like, I need my electrons back. Silver, I can get them back from you, and we can reverse this. Or carbon, I'm going to take them from you. And I'm eager to leave now. And what does that give? It gives us our carbocation, which we're looking to form faster. And the silver ion could increase the rate of this reaction. What else could we form here? Silver bromide. And what do you know about the solubility of silver bromide? Hopefully you know it's insoluble. And this will actually, what does the arrow mean? Down arrow means precipitate? Yeah, it will actually precipitate during the reaction. And you can go through this. I'm showing elimination product. Something takes the H to put in the double bond, right? Takes it. What takes the H in this? Apparently what took it? The nitrate anion I showed taking it. And if you do that, you're going to form nitric acid. And the water actually didn't do anything here. The water was just a solvent. In actuality. And what type of mechanism did we do here? We eliminated, right? E1 or E2? E1. E1. But we increased the rate. This is going to make the bromine more eager to leave. Lewis acid, okay? But this can also be used as a chemical test because you can see this precipitate. You're only going to see that precipitate if you formed a carbocation. Because it's only going to form silver bromide if that leaves. You're only going to get that if that leaves and you get a carbocation. So ultimately, as it says at the bottom, if you see silver bromide forming, that means your halogen was ionizable. The first question is really, which of these is the halide ionizable? We're out of time here. Please answer those questions. We'll finish up this quiz on Monday or after Thanksgiving. I'm sorry, test.
After Thanksgiving.
Who says after Thanksgiving? Okay, that's yeah. I think that's best. And what I like to do is, all you gotta do is just act like it's Monday, study, and then you're ready on Monday, and then take your time and just have it a week later, and you have time to follow up. Okay. But because of that, we can we'll have a little more time to finish up, and we should have a quiz on. We'll do the quiz on this Monday. And on this Friday, we'll finish up this and other loose ends. And then after the quiz, we may have lecture on UV Viz. Have a good